In this lecture, we're going to learn how to calculate equilibrium constants from experimental data. If we can measure the equilibrium concentrations of all reactants and products for a reaction, then we can calculate the value of the equilibrium constant. For example, consider the reaction of nitrogen plus 3 hydrogens going to 2 ammonia gas at 472 degrees Celsius. The equilibrium partial pressures are found to be 7.38 atm hydrogen, 2.46 atm nitrogen, and 0.166 atm ammonia. Calculate the equilibrium constant under these conditions. First, we begin by writing our Kp expression, which is written in terms of the partial pressures of the different gases. Our numerator contains the partial pressure of ammonia squared. Our denominator contains the partial pressure of nitrogen times the partial pressure of hydrogen cubed. At this point, we know the individual partial pressures, so we can substitute them in directly. 0.166 atm for the ammonia, 2.46 atm for the nitrogen, and 7.38 atm for the hydrogen. At this point, we can complete the calculation and find that our Kp value is 2.79 times 10 to the negative 5. In some cases, we can only measure the equilibrium concentration of one or two species, but not all of them. Are we able to calculate the value of the equilibrium constant under these circumstances? The answer is yes, as long as we know the initial concentrations of all reactants and products and the equilibrium concentration of at least one species. We will make use of a structure known as an ice table. The name will become clear when we build our first example. There are 5 steps that we need to follow in order to calculate the equilibrium constant for a reaction. Number 1, we need to tabulate all known initial and equilibrium concentrations. Step 2, if you know both the initial and equilibrium concentrations for one species, and this can be either a reactant or a product, calculate the change in concentration for that species. Step 3, use the stoichiometry for the reaction to calculate the changes in concentration for all other species. Step 4, calculate the equilibrium concentrations for all species using the initial concentrations and the changes in concentration. And finally, step 5, calculate the value of Kc using the determined equilibrium concentrations. Here's an example. A container of 1 times 10 to the minus 3 molar hydrogen gas and 2 times 10 to the minus 3 molar iodine gas at 448 degrees Celsius is allowed to reach equilibrium according to the reaction H2 plus I2 going to 2HI. At equilibrium, the concentration of HI is found to be 1.870 times 10 to the minus 3 molar. Calculate the value of Kc. The first step in this problem is to build the ice table for the reaction. Notice that the top row of the table is nothing more than a restatement of the chemical equation for the equilibrium. There are 3 additional rows. The first row lists the initial concentrations of each species. The second row lists the change in concentration for each species, and the third row gives the final equilibrium concentrations of each of the species. Notice that the initials ICE give name to the ice table. We can now follow our 5 steps in order to complete the calculation. Recall step 1 is to tabulate all known initial and equilibrium concentrations. Returning to the problem, we see that we initially have 1 times 10 to the minus 3 molar H2 and 2 times 10 to the minus 3 molar iodine. Additionally, we see that at equilibrium, we have 1.870 times 10 to the minus 3 molar HI. We can now add these values to our ice table. Note that it seems that we may have a problem at this point. As indicated, we must know the initial concentrations for all species in addition to the equilibrium concentration for one. We have no information regarding the initial concentration of the HI. In this case, because we're not told an initial concentration, we have to make the assumption that the initial concentration of HI is 0, indicating that we begin with nothing but H2 and I2 and are forming HI throughout the course of the reaction. This is a common assumption that has to be made. Step 2 tells us that if we know both the initial and equilibrium concentrations for one species, we can calculate the change in concentration for that species. Since we know the initial concentration of HI is 0, and its equilibrium concentration is 1.870 times 10 to the minus 3 molar, we can calculate the change by taking the difference. This indicates that we must increase the concentration of HI by 1.870 times 10 to the minus 3, and we can enter that value into the change row. The next step is to use the stoichiometry for the reaction to calculate the changes in concentration for all other species. In order to do this, the changes in H2 and I2 must be calculated from the known change in HI concentration. To calculate the change in H2 concentration, we begin with our change in concentration for HI, 1.870 times 10 to the minus 3 molar. We then notice from the chemical equation that for every 1 mole of H2 that is consumed, we form 2 moles of HI. We can then include this stoichiometric factor and perform our multiplication to show that we have a change of 0.935 times 10 to the minus 3 molar H2. Please note that your calculator probably states 9.35 times 10 to the minus 4. This is an equivalent value. I have chosen to keep the same power of 10 for ease in reading the table. When calculating the change in I2 concentration, we once again begin with our change in HI concentration, 1.870 times 10 to the minus 3 molar. Looking at our chemical equation, we find that for every 1 mole of I2 that is consumed, we form 2 moles of HI. This again forms our stoichiometric factor, and when we perform the multiplication, we once again find that 0.935 times 10 to the minus 3 molar I2 is consumed. When we add these two values to the table, we have to include a negative sign because the reactants are being consumed in this case, and so the concentration decreases. Step 4 requires us to calculate the equilibrium concentrations for all species using the initial concentrations and the changes in concentrations calculated in Step 3. In order to accomplish this, we merely read down a column and perform the required arithmetic. For the H2, we begin with 1 times 10 to the minus 3 molar, and then we subtract off 0.935 times 10 to the minus 3 molar, resulting in 0.065 times 10 to the minus 3 molar at equilibrium. Again, please note that your calculator probably reads 6.5 times 10 to the minus 5. This is an equivalent value. For I2, we begin with 2 times 10 to the minus 3 molar, and decrease by 0.935 times 10 to the minus 3 molar, leaving us with 1.065 times 10 to the minus 3 molar at equilibrium. We now know the final equilibrium concentrations for all 3 of our species. Our final step is to calculate the value of Kc using the determined equilibrium concentrations. Our Kc expression includes the concentration of HI squared in our numerator and the concentration of H2 times the concentration of I2 in the denominator. We can substitute the values in from the equilibrium concentration row of our table and calculate that our Kc value is 50.51. Now that we've seen one example, let's work a second. A container of 5.25 times 10 to the minus 2 molar ammonia is allowed to reach equilibrium according to the reaction 3H2 plus N2 going to 2NH3. At equilibrium, the concentration of N2 is found to be 1.25 times 10 to the minus 2 molar. Calculate the value of Kc for this reaction. Again, our starting point is to build the ice table for the reaction. Our chemical equation is restated as our first row. Beneath that, we have our initial concentration, our change in concentration, and our equilibrium concentration. We can read from our initial problem to tabulate all known initial and equilibrium concentrations. In this case, we are beginning with ammonia, 5.25 times 10 to the minus 2 molar. The only equilibrium concentration we have is the concentration of nitrogen, which is 1.25 times 10 to the minus 2 molar. We can substitute these two values into our table. It is clear that we have no indication of the concentrations of H2 or N2 initially, and so we must take these two values to be 0. Notice that this means that the reaction is back-reacting, causing the NH3 to decompose into H2 and N2. In our second step, We look for the species for which we know both the initial and the equilibrium concentration. In this reaction, that happens to be the nitrogen. We begin with 0 molar nitrogen, and at equilibrium we have 1.25 times 10 to the minus 2 molar. This results in an increase of 1.25 times 10 to the minus 2 molar as our change in concentration. Again, step 3 uses the stoichiometry for the reaction to calculate the changes in concentration for all other species. This time we are calculating the changes in H2 and NH3 using the known change in concentration in N2. For the change in H2 concentration, we begin with the 1.25 times 10 to the minus 2 molar change in nitrogen concentration. According to the chemical equation, for every 3 moles of H2 that are consumed, we also consume 1 mole of nitrogen. This provides us with our stoichiometric factor of 3 to 1. When we multiply, we find that our change in H2 is 3.75 times 10 to the minus 2 molar. Likewise, for NH3 change, we begin with the 1.25 times 10 to the minus 2 molar change in nitrogen. According to the chemical equation, for every mole of nitrogen we consume, we form 2 moles of NH3. When we multiply, we find that the change in concentration of NH3 is 2.50 times 10 to the minus 2 molar. These values can now be added to our table. Notice that because we are back reacting, the concentration of NH3 decreases, meaning that we need a negative sign on that change. And the change in concentration of H2 is positive because we are forming H2 during the back reaction. We can now calculate the equilibrium concentrations for the remaining species from their initial concentration and the changes in concentration. Again, we just read down each column and perform the required arithmetic. For the H2 column, we begin with 0 molar, and we increase by 3.75 times 10 to the minus 2 molar, resulting in an equilibrium concentration of 3.75 times 10 to the minus 2. In the case of the ammonia, we begin with 5.25 times 10 to the minus 2 molar, and we decrease the concentration by 2.5 times 10 to the minus 2 molar. This leaves us with an equilibrium concentration of 2.75 times 10 to the minus 2 molar. We are now able to calculate the value of Kc using the equilibrium concentrations as calculated. The Kc expression includes the ammonia concentration squared in the numerator. The denominator contains the H2 concentration cubed times the concentration of nitrogen. Upon substituting these values and calculating, we find the value of Kc for this reaction to be 1.61. This concludes the lecture on calculating equilibrium constant values from experimental data. In conclusion, there are several things to remember. 1. If you know the equilibrium concentrations for all species, you can immediately calculate the equilibrium constant value without the use of an ice table. You merely substitute your equilibrium concentrations into your Kc expression and calculate directly. 2. You must know the initial concentrations for all of the species and the equilibrium concentration for at least one species to calculate the equilibrium constant value in general. 3. If you are not given an initial concentration for a certain species, you can only assume that the initial concentrations for that species is 0 molar, or in the case of partial pressures, 0 atm. Remember that anytime we use Kc in this lecture, we can easily substitute in Kp as long as we use the partial pressures rather than the concentration.